Now let's get ready to be inspired by the next career advice.
So what do we have next?
So now we move on to the Pyroboplan session.
Yes, because one of the basic skills of robots is the control of a robotic, skillful robot, is to control a robotic arm. Robotic arms are everywhere in industry, so understanding how they work, it's like a basic skill that you must possess if you want to work in robotics. So in our next speaker is Sebastian Castro, and he is a robotics engineer and educator. He has created recently a Python library to better understand how robot arm motion planning works. Today, Sebastian will guide us through robot arm motion planning with Pyroboplan. Welcome to the conference, Sebastian.
Hello, Ricardo, and hello, everyone. Thank you for the opportunity to speak here.
Yes.
It's a pleasure.
Hello, nice to see you again. And then, do you have your presentation ready? Your project, your
We are
project?
ready. So I should be sharing my screen now.
We can see it. So the audience is all yours.
Perfect. All right. For those of you in Europe and east of that, I commend you for still being awake. I will try to make this as exciting as possible. I'll also try to hear the chat. It seems I'm too quiet from what I'm seeing. So let me see if I can modify my input volume. Am I a little bit louder yet? Is that any better? Hopefully that's okay.
Yes, a bit better.
All right, wonderful. Okay, so while the ROS check loads, you're going to see a bunch of things running here on the terminal on the right. So hopefully your installation is complete by the time we're done with the introduction. So I'll tell you a little bit about myself and about kind of what this presentation is about. So as Ricardo said, I'm going to be talking through this Python-based educational tool I made called Pyroboplan, which we'll spend a lot of time with. And I'll tell you why I made that and where it fits into the ROS ecosystem. Because one thing you're going to need to know from this talk is that we're going to be using zero ROS. So how does this come together? So let's get to that. So this is a little bit about me, right? I'm currently working at the AI Institute, which is a research offshoot that spun up from former Boston Dynamics founders. But in my career, since I started working in 2011, I've been kind of oscillating between the areas of education and then actually, working in different kinds of companies, some larger, some smaller, some more focused on software, some more focused on product. So one thing that's always on the back of my mind is that making robots do something that we can easily think about ourselves is actually really hard to implement. And of course, there's been a lot of tools that have come out to make this easier, not the least of which is ROS. But I still think that overall, I think a lot of us as roboticists want to start solve problems, and sometimes it can be a little tough to kind of be stuck in the software land just to like learn things or iterate on things, come up with prototypes. So that's really been my motivation. There's a lot of great ROS frameworks for doing motion planning with robot arms. You might have heard of tools like Move It or Tesseract, or even equivalent frameworks in other areas like Nav2, for example. These are all very capable tools. They're very extensible. They let you create plugins for customizing. They connect very much with other pieces in the ROS ecosystem. So these tools are very good for getting something working and talking to a robot. But even if you've seen the talks, that we've gone through today, we haven't needed to worry very much about how the actual algorithms are implemented. And I think that's a good thing, right? I think it's great that with all these ROS tools, you can basically, grab your EKF package and have something working with only configuration files. That's like a big power of ROS. But sometimes, especially as newcomers, either because you're more junior or because you're learning a new area, sometimes it does pay off to have tools that maybe are a little less targeted to that and something that facilitates your own educational experience. So that's where Pyroboplan comes in. This is kind of my trying to figure out how these motion planning libraries work for manipulators and giving people hopefully easy to use platform for that. So hopefully I've spoken enough that people's installations are complete. I am seeing the chat. So if people want to say whether they're still installing or they're complete, I'll be looking at the chat log as well. But as it says here in the notebook, when the installation is complete, you'll be able to see this installation complete on the terminal on the right, and now we can actually start opening stuff. So let's just open one quick example to check that we've kind of loaded things up correctly. One thing that this requires is that because of the visualizer that we use, we need to use Google Chrome, and there's some interesting artifacts in making that work here. So if you scroll down to here, open up a new tab and do sudo Google Chrome no sandbox. That will get Chrome to spin up in these ROSjects. And once you've run this command, you'll see that the graphical tools will appear, and you can kind of blow through all these prompts. You don't have to sign in. We recommend not doing that. But eventually you'll get a Chrome window that we can use to actually look at our visualization. So hopefully you've gotten that set up. As far as running our examples, I'm actually going to go back to the terminal here, and what we'll do is we're going to change folders to the Pyroboplan/examples folder. And then here you'll see that we have a bunch of Python examples you can run. These are the ones that we're going to use for the duration of this material. You can also go to your IDE, and under Pyroboplan examples, you also have access to all of these right here. Okay. So when we run these examples, we'll get to kind of look at the code a little bit and see how this stuff works. So let's talk first about how we can model our robot arms. So the first example we're going to run here is this intro Pinocchio manual file. This tool was made by reusing existing libraries that already let you model robots. And if you haven't heard of it, there's a really great library called Pinocchio that basically gives you the ability to create these rigid body articulated robots, do things like kinematics and dynamics. And Pinocchio is actually available in the ROS ecosystem, so you can depend on Pinocchio as a package and then use it both in C++ and Python. So I'm just going to share with you a few basics here, and we'll explore how this works. So we're going to run this intro Pinocchio manual example. Again, we're going to navigate to our examples folder. We're going to run this, and you'll see that as we run this file, at the very beginning, it'll tell you that you can open the visualizer by going to a particular website. And this website will pretty much stay constant for the duration of the presentation. So if I type in 127.0.0.1/static, oops, I missed the 7000. Remember the slash at the end, otherwise you don't get the page. And I must have forgotten something here because the example is still not loaded. Let me go again. Sometimes it's also that the example actually finished running by the time I spoke. So sometimes you can also bring it up and refresh. Okay, so if things show up correctly, you should see some visualization like this. Let me know if you guys are able or not able to see it. But this is just going to pick a random position for your robot and display you a couple of things, right? You'll see in this whole visualizer, the reason I'm bringing up this basic example is twofold. One, you see that our robots, the very basic way of modeling robots is that we can create these little assemblies that have rigid bodies like boxes or cylinders or spheres and connect them together with links and joints. And as you expand this mesh cat thing on the right, you can actually look at the names of the individual bodies like link 0, link 1, and you can enable and disable them. So you actually have full access to seeing what links are on your robot and so on. Same thing for the joint frames, right? So joint number 2 is at a particular place on the arm, and then so on. So this is kind of the basic things that Pinocchio lets you do. You see if we open up our IDE, These models are all made programmatically, so you can manually do things like adding links and joints and defining transformations and shapes, etc. Okay, but very often we don't define robots programmatically like this. If any of you have been working in ROS for more than maybe half a day, you'll know that there's other formats like URDF models, right? And indeed, most motion planning libraries do ingest that. So there's another example here called Intro Pinocchio UR5 Sim that you can run. And you see this is actually going to load directly load a URDF file from one of the packages that we've included that's also contained in this folder. You see it's under here in the UR description. So let's run this one instead. This one is called Intro Pinocchio UR5 Sim. And if we go back to our browser, you'll see if I refresh, I now have an actual universal robot that's going to be moving around, and there's a lot of things displaying on the screen. It's printing frantically, just to kind of show you what's going on, right? One key thing here is once you load these models, you'll notice that there's now, if you expand this, there's both a collisions and a visuals model, right? So usually for these manipulators, you have a model of your visuals meshes that has the full quality meshes. And then you also have collision meshes, if I uncheck and check the other one, which are usually more simplified meshes that are easier for collision checking. And so then you also see these green lines that show you the distances between non-colliding parts. And there's also actually sometimes the arm will cross itself, and you'll see some red displays showing the parts that are in collision. So what I'm getting to is that when you're working with these models, you're usually loading from these URDF files, whether it's in these libraries or things like Gazebo or MoveIt, where you have this robot, where you've defined, things like links with visual geometries and collision geometries, and the tool can kind of ingest that as well. So that's like my as quick as possible crash course to robot modeling. Again, if anyone has questions, I will still be monitoring the chat as I go, but we can also save some for the end. So this is basic modeling, right? Like we have a robot that we can do basic kinematics and dynamics and collision checking, but at the end of the day, we're here for motion planning. So let's dig into some of that stuff. I'm gonna stop the script. So and let's look through the notebook. Okay, so those are some of the basics of modeling. I'm actually gonna skip some of these other ones, but you have the ROS checked available. Just something that showed you that you can do collision checking along a path. But let's talk more about motion planning, right? Critically, when you're talking about motion planning, there's lots of different ways to mix and match it. But I recently drew this diagram that kind of shows the classical steps of how you go from getting your robot to move from one point to the other, right? When you're commanding your robot, you're either telling it to go to a particular joint position, or you're giving it a pose. So this is like an XYZ and rotation of like some part on the robot, like the gripper. Sometimes you need to convert that to joint positions by doing what's called inverse kinematics. So we'll look at that very quickly. And then at the end, you're trying to move your robot to a particular location, a particular joint configuration. The thing is, you usually can't just move in a straight line because you might hit things. So you might, collide with the robot's links themselves. You might collide with the environment. So path planning needs to account, what is a feasible way to move to your goal without hitting things. But that only gives you a path. You then need to take into account limits on your robot, like if you have like velocity limits or acceleration limits, torque limits. So you now have to convert that path to something that the robot can actually execute as a function of time. And that's what trajectory generation is. And then once you have a trajectory, which is like basically the positions, velocities, so on of the joints over time, you can finally take you go to your robot controller and run things. And this is where things like ROS are very useful, like the ROS2 control package. So we're going to spend the rest of this talk just going over some of the examples for each of these components. Well, at least for the inverse kinematics, path planning, and trajectory. Because this is a simulation library, we don't really have much on the control side yet. So let's talk about that. So again, inverse kinematics this is a lot of math here, but bear with me. Inverse kinematics is the problem of saying that you want a particular part of your robot to move somewhere else, and you need to figure out what the joint angles are to achieve that. For some robots, it's very easy to do the math for that. For other robots, it's not. So there's lots of different algorithms that achieve this, and we're just going to go through one of them and just kind of show you how the tool lets you explore these things. So what I will do, under the examples, we're going to run the, as it shows on the notebook, we're going to run the Python script differential ik.py, which is actually the algorithm you see on the screen. And when you run this and open up your browser, you'll see now, hopefully this looks okay over the presentation, but basically you have your robot living in the world, and then somewhere there's going to be a coordinate frame for the target pose that it's trying to get to. I'm trying to find it. Oh yeah, it's over there. So you see, you basically have your robot solving over time, and it's trying to move one of the coordinate frames into the other one, and showing you on the script whether your robot solved it, or is it inside or outside joint limits, is it in collision, and you get a couple of retries. This is done completely randomly, so it'll pick a random pose. For you, you might have gotten a configuration like this. For others, it may take a few tries, and then the script just keeps running and tries a bunch of random poses to see how you can solve inverse kinematics from one point to the other. So going to the IDE, you can see that the way that these examples started working with motion planning is that you load a model, and then you have these relatively basic classes like, differential IK options, and you can just run them. You can, plot different things about them, display them on this visualizer, and so on. And when you want to go to these implementations, the actual library is the one that has the, the actual code. I'm just going to open the code for one of these just to show you that the code has, a lot of comments explaining the parameters, but also links you to resources for, where the papers this was implemented from. It also gives you, as you go on, information about, what are the mathematical steps that are happening. So hopefully this helps you learn, or even, quickly modify your algorithms in Python to see how motion planning works for you. So yeah, again, there's many ways for inverse kinematics. This is where I will also start plugging a little bit and saying that, I've only implemented one IK algorithm so far, but the idea is for this tool to be, fully open source. So if people want to try their own algorithms or variations, you can contribute to this library and share with all your robotics peers. Okay, so inverse kinematics is one thing. Again, this is just showing you the progress of this optimization to move to your target pose. Suppose you've already done your inverse kinematics, right? Next, we're going to get into the actual path planning, which I think is probably the one that that we want to spend most time on. So one of the classical ways of doing motion planning, and this is actually one of the key features in MoveIt, is this notion of sampling-based motion planning. This is where if you're trying to move your arm from a start to a goal, you basically are, doing some kind of planning where you're trying to go from start to goal without hitting obstacles in this high-dimensional space of your joint angles. And there's really two main flavors of sampling-based motion planners. If any of you have heard of them, these are probabilistic roadmaps, or PRMs, and rapidly exploring random trees, or RRTs. And these have some slight differences. The big difference being they both kind of look the same if I just scroll into this picture. They all sample a bunch of points until you get a collision-free path to go from point A to point B. That's a constant. But if you look at the probabilistic roadmaps on the left, are a lot more, they have a lot more points on the graph, but you can actually reuse them. So they're called multi-query planners. It means that you can actually generate this big graph and use it for like multiple motion plans. And then on the RRT side, these are less dense, but they have a finite lifetime. So when you plan an RRT, it only plans from start to finish, and then you throw away the planner. So I will go back and I'll show you some examples of this. We're going to start with a simple robot just to give you the contrast. So if you guys run there's an example called PRM2.py. So it's going to run the probabilistic roadmaps for a 2 degree of freedom arm. And this one takes a little while to load, but I'm just going to refresh. And you see I have this arm that lives on a disk. And then you have these, you can actually turn on and turn off different things like the actual graph and the planned path. So you can say, oh, you know, this I see how this path looks like. I'm going to go from one point to the other. So I'm going to hit enter and animate the path. Robot's going to move without hitting that green circle. And then this is kind of like an addictive game. You just keep pressing enter and it's going to plan to you a new path to go to. And then it's going to plan over there. So you can feel free to play around that with your ROSject or install locally as you want. So this will just keep going, right? Again, the key thing is that you saw that the script took about 5 seconds to start, but the subsequent planning was really quick because you're just reusing that graph and just doing search. Let's do that in contrast with the other example, which is the our other sampling-based motion planner, which is the RRT, or Rapidly Exploring Random Trees. This one, again, I'm just going to refresh that. So this one, you see it generated this, it's a much more sparse tree, but you can see what's happening. And actually, in this case, planning timed out because it couldn't find a path from start to finish in the time allotted. So I think I'm getting unlucky with this one. Sometimes there's these little nooks that you can't really hit with the RRT. So you see it's trying. At some point, it might get a valid path. If not, then I might just restart to get a new random target goal, which I think I might do just. So maybe you are seeing some paths. Okay, so this one you see, this one didn't actually have to sample a bunch of nodes because RTs are interesting in that they can like bias you towards the goal. So you don't have to sample the entire workspace, you just kind of sample towards it. You see here, you're running through the path and it works great. And then you can keep planning. You see you get a new path. This one's really trivial, so it barely did any planning. So as you keep trying different ones, you might get more complicated trees. You know, you might have noticed some things that with sampling, it's you get these like really weird paths that look very not optimal, and that's kind of the downside of doing sampling-based planning, right? But there are tricks that we can use to get around that. But I'm gonna, yeah, let's try those out. So if you go to your IDE and you open up that RT2.dof example, I want you to look at these options. And there's actually a couple options we can use to make the plan quality look better. If you go in here and you change a couple of options, so I'm going to set bidirectional RRT to true and RRT star to true. These are some variations of the RRT algorithm that are documented also in the implementation. These are going to do stuff that improves the quality of motion plans by doing two things. But I'm just going to rerun to show you what that is. So firstly, the notion of bidirectional trees means that you're now going to do planning with trees, two RRTs. So one tree starts from the goal and goes backwards. The other tree goes from the start point and goes forwards, and they try to meet each other. And you see that that's where the pink and the blue trees kind of converge on each other. The second thing is this RRT star. You notice now that the tree looks way less jagged because RRT star actually, you know, once you sample a tree, it tries to like rewire it and then tries to like create shortcuts in the plan. So you can get something that is less, you know, wonky and moves around a lot. So these paths look better, but they still have the characteristics of, you know, you're just at the end sampling a bunch of stuff. There's a lot you can play with these tools. You know, the cool thing is that this doesn't just work for a 2 degree of freedom robot. If we instead run the, if instead we run the RRT example for the Panda robot, which is a 7 degree of freedom robot, you can actually do exactly the same thing, but visualize it in a higher dimensional space with 3D obstacles. So now, you know, you see here planning timed out again for me because I must have picked a bad pose. But maybe when we try a different random seed and refresh, you see that sometimes the RT does give you solutions. Again, you see this path is basically like a three-dimensional sphere version of what we saw before, but it just looks like this hideous, you know, like almost traversing a globe in a really awful way. But you can apply the same tricks as we just talked about, right? If we go to the same RT Panda example, I can also turn on the bells and whistles, like turning on the bidirectional or the RT star. I can rerun that, and hopefully now, if you try again, you get paths that look a little bit nicer. They still have some issues, but you can see this looks maybe closer to what you would expect your robot should do. Yeah. So hopefully you can play around with that. There's lots of other types of motion planning, so we're not going to stop there, because there's a couple of things that we need to talk about still. So we have these paths, right? In all these animations, I'm just basically picking a constant velocity for the robot to follow the path in. But we know that that's not necessarily feasible because your robot might actually have limits associated with them. Like we talked about things like maximum velocities or maximum accelerations. So that's where you get into the area of trajectory generation. Trajectory generation is kind of, again, what you need to bridge between your path planners and your controllers. And there's a couple of different ways that most people do these. The two that have been more standard classically are these two that you see in the diagram. You have trapezoidal velocity trajectories and polynomial trajectories on the right. They both have their benefits. The trapezoidal velocities are very easy to implement because they basically follow a very rigid rule of like going as fast as possible, staying at the fastest speed, and then decelerating. But they leave a lot of optimality on the table. They're used a lot in industrial arms because they're very easy to do. Polynomial trajectories, on the other hand, have more smoothness properties. Like you see, for example, depending on like higher orders of the polynomials, you can have you can get away with like discontinuous accelerations or discontinuous jerk. But they also are a little bit. You need to figure out exactly what the boundary conditions are. In both cases, really. So both the examples that you see here are doing a trajectory with two segments that is basically starting and stopping at 0 velocity, and that's how a lot of these work. We can actually run that. So if you look at the, we have an example here called trajectory generation.py. And when you run this example, you can configure it to either run a trapezoidal or a quintic. This is a, maybe I should write this. This is a 5th order polynomial trajectory. So you can choose whichever one you want. I'm just going to start with the trapezoidal trajectory, and I'm going to give it limits of maximum speeds and accelerations of these values, right? You can play with those if you want to see if you can make your arm go faster or slower. But let's run that. So this one is called trajectory generation. And then I'm just going to refresh the page. Well, actually, before refreshing the page, this now starts bringing you plots. And if you watched Tesas's talk, this is also the same matplotlib library that I'm using here to display the trajectories. So this gives you the joint motions for the joint trajectories for each of your joints. Like Panda joint 5, Panda joint 4, etc. And you can validate whether you've met your min and max accelerations, for example. If I find my browser. Again, I have to refresh Meshcat. This one will just show you that your trajectory just tries to go across 3 points. So you see you've got those 3 coordinate frames existing there. And when I hit enter to animate the path, it's going to start, accelerate, then decelerate at the middle point, and then accelerate again from the middle point towards the final point. The trapezoidal and the quintic look slightly different. You're not really going to be able to maybe tell very much over this presentation, but maybe certainly the plots look different, right? They don't have that trapezoidal velocity. They are now like 5th order smooth polynomials, so the acceleration is also smooth. And when you run this trajectory, it might actually end up looking very similar. Oh, I didn't refresh the page. I'm sorry. I'm gonna have to run that again. Okay. So again, it just picks random points, but this might look the same because you're, again, starting and stopping at 0, but just the profile looks slightly different because it's not trapezoidal velocity. Okay. So there's two other things about trajectories that I want to talk about before concluding. I know it's a whirlwind tour, but I'm going to give you a lot of resources to do more. So two problems, right? Actually, when we ran, I'm going to run the RT example again because I want to show you something. When you do these RT plans, whenever you're doing any kind of segment in your path planner, it's actually a straight line in the joints of the robot. However, because the robot arm kinematics are not linear, a straight line in joint space actually is not a straight line in like the real world. It has no ROS dependencies. That's correct, Anderson. It's fully Python installable. Yeah. So what if you actually do want your robot to move in a straight line in the real world? Like if you're trying to do like a painting task or welding or something like that, you're going to need another set of techniques. And actually, there's a very common method that's called Cartesian space planning. I guess I flipped this backwards, but just scroll down to the Cartesian planning part of the script. One thing you can do is actually do all your trajectory planning in the Cartesian space. So in other words, the X, Y, Z translation and rotation. And then for each step in your trajectory, you basically solve inverse kinematics from one step to the other. So you actually get the modified joint trajectories that give you a straight line Cartesian path. And this is something really common to do in robotics. So I believe this is just called Cartesian path.py. You can run that. And if I refresh, you will again get this little window. This is actually, I have a really small story to share with you here. When I hit animate on this Cartesian trajectory, you see this like vertical line that's moving with time? I think that's really cool. This is actually some random person that I didn't know that just saw my repo and was like, hey, I really want the straight line. Submitted a PR, we got it in. So I really like seeing these kind of contributions. So yeah, you can see your robot is like tracking an actual set of straight lines. So that's fun. Yes, and I believe it was at the last MoveIt that some of the construct folks presented on their new Cartesian planning class as well. I know you guys had a smaller bite-sized section as well. Cool. So actually, the method that I just showed here is very similar to how MoveIt would do it, right? Where you try to solve inverse kinematics for lots of points along an actual straight line. Okay. So there's one more thing that I want to talk about in the next 5 minutes before wrapping up. And that is, in both of these trajectories, we noticed that there was one thing that was not ideal, which was, why did we, if we have two segments in your trajectory, why did we can set any speed we want, but how do we know it's a good speed? So there's been lots of techniques recently that do trajectory optimization, where you actually try to optimize the parameters of the trajectory so that you basically try and minimize the time it takes for your robot to safely track something. There's lots of methods to do this. What I'm doing here in this library is I'm using the tool called Drake from Professor Russ Tedrake's lab at MIT, if any of you are familiar with that. But you're actually able to take these trajectories and put them into an optimization problem, which I think is really cool. So you can run this trajectory optimization example. When you get these plots now, you see that all the trajectories basically are like maximizing their velocity as much as they can, and they're not stopping at 0. So you actually get trajectories that, even though they have, in this case, I think it's 7 segments, they're basically optimized to minimize time while meeting the velocity, the acceleration, and jerk limits of your arm. So if you run this, you've got this. Oh, did I hit enter? Yeah, you've got this path now that is way snappier than before. It like really accelerates at the center and then slows down only at the endpoints. And then it just keeps going. Last thing I will say is that there's also a way to combine these things. So there's one last example, which is called optimize RT path. So what if you could take a path from an RT as we saw, it was not necessarily the most optimal path. And then you try to put it through a trajectory optimizer to get a full trajectory. So indeed, you can do that. You see you've got these like funky looking joint trajectories here. And if this wants to load, oh, somehow the address changed. So now it's 7001. But now if I do this, you see you've got your basically your RT path and your optimized path. They're shown side by side, but you can go into MeshCat and basically, turn off either the planned path or the optimized trajectory, and you can see how different they might look. Where the planned path has this like swirl, but maybe the optimized maybe looks the same, but it did optimize it to at least not have 0 velocities at the endpoints. And then you'll see your robot basically doing the whole following of this, while hopefully avoiding collisions. This one looks like it's going to get close to collision. So yeah, I guess the big takeaway, because I know I have 3 minutes, is that there are a lot of features here for you to kind of play around with trajectory optimization, path planning, all the different flavors. It's fully done in Python, no ROS, so you can just import your model, try things out, and hopefully make contributions. I'm going to say one set of concluding remarks, though. At the end of the day, I do think you need this to run on a robot, right? And this tool is not going to do that. It's also written fully in Python, meaning that it's going to be very not performant compared to some of these tools like MoveIt, which are written in C++ for a good reason. You saw that like my RRTs here were timing out after 10 seconds, which would be an offensively long time for MoveIt to do an RRT. Like that should really take no more than a few seconds in these, or like even, it shouldn't take more than like 1 second on these relatively easy problems. So I think the goal of this tool and tools like this is for you to kind of learn the basics so that when you go into these frameworks like MoveIt or Tesseract, you actually maybe know what you're looking for. You understand the role of the motion planning in the bigger scheme, where you have to then take this trajectory, send it over to a ROS2 controller, etc. So, I think that there's room for all of these tools. It's just a matter of what your focus is at the moment. Are you prototyping? Are you trying to learn? Are you trying to introspect? Or do you actually want something to work on real hardware in real time? So definitely check that out. If you want to know more, I have the Pyroboplan repo is fully available. I see someone already linked it, which is great. And if you want the not abridged version of this presentation, I recently wrote a full blog post that is very, very long, but talks about this in lots of detail and links you to a ton of resources for learning both the mathematical foundations, the software tools that exist, and other common algorithms you might have. So definitely check that out. You have the ROS Direct available, you have Pyroboplan, you have my information if you want to talk to me. Thank you for making it through that. I finished on time, shockingly.
Excellent. Excellent. Sebastian. Yes, it looks like you were on the second there. Excellent. So now it's time for the audience to ask you questions, and for that we have the Q&A section tab on the chat, where you can put your questions to Sebastian or both, the ones that somebody else has put it there, and then I will be asking to him the questions. Okay, great, excellent. Okay, so excellent. So we have one from Thesis, one of the previous speakers, and has been one of the most voted here so far. Then it says, could I try to run this on a real robot, like, for example, ABB?
Yes, absolutely. So I mentioned this a couple of times during the talk, that I mentioned ROS2 control a lot, and ROS2 control, which is maintained by Dennis Stogel, which did one of the first talks here, among other folks. It really plays into the modularity of ROS. So what I would do if I had to use this tool and send it a motion plan to a robot, I would package up the resulting trajectories from this tool. I would put them into a ROS trajectory message, and I would send them to my favorite ROS2 controllers. Lots of different robots like Universal Robots, Kinova, etc. have ROS2 controllers already available. I'm not sure about ABB, but if it does, it makes that a lot easier.
Okay, yeah. So now I don't know that's ABB if it has drivers for ROS, but yeah, does it? Do you think? Yeah. Okay. And then the important point here is that the trajectories that are generated by the Pyroboplan, then they can be used and transformed into messages of ROS messages. I mean that you can send to ROS to control.
Yeah, and I think someone was talking in the chat about the no ROS framework. I think that the way to design these tools is something like this, whether it's in Python or not, where you have this like tool that you don't need ROS for, but if you do want it, you could write these wrappers that can do the right data type conversions and put things into ROS nodes. So you get the best of both worlds, right? You have something easy for prototyping and something that can talk to your hardware.
Okay, excellent. Let's go for another question here. So Robert Cowher says, how does this type of path planning compare to reinforcement learning methods? Could you elaborate on the learning methods here, specifically how it picks the appropriate path from the various sample options? Can it tweak sorry, an existing best option, or is improvement just continuing or to random sample?
Oh, well, that's like, that question is basically a whole history of the history of motion planning, right? Because the first ever implementations of sampling motion planners were, you know, the very stupid thing as you described, right? Which is just keep randomly sampling, maybe something better will come along.
Oh, yeah.
Then there have been variations on these planners that actually try to use some real information to try shortcut paths. And the thing about these methods is that, you know, it's hard to get them to do something very optimal, but you know, because you're actually implementing these algorithms, you're checking collisions, you can guarantee that the paths will at least meet the requirements that you're validating against. With machine learning methods, they can do very impressive things, but you need to similarly find a way to validate them, right? There's been lots of ways to use RL to accelerate planning in lots of different ways. I recently saw some places that try to, you know, use, I think it's a really good use. They try to use machine learning to do faster collision checking by using, basically having a learned model generate these like signed distance fields for collision. So you don't have to like do these expensive, you know, polygon mesh collision pairs. You just like trust that your learning algorithm does stuff right. It comes with risks, right? So I think that the key behind the RL methods is that you need to validate them anyway. Sometimes they'll do good things, sometimes they won't. I'm a big believer in if you have the compute to like try to compose them in different clever ways or even try to run them in parallel. So like if the learning algorithm doesn't give you anything good, you can fall back on a more, you know, old school planner that at least does the job. I think ultimately in robotics, the biggest goal is to make sure the robot doesn't get stuck and can keep moving along even if it's not quite as optimal as you want it to be.
Yes, to get stuck into a position from where it cannot recover.
Exactly.
Yeah. Okay, then another question from Got It. Got it. Yes, interesting name. So, how do you define the joint limits, the obstacle avoidance, and the path? Did you use a behavior tree for that?
No, this is completely below the behavior trees, right? So the behavior tree can do high-level planning. So everything that I showed here would kind of be below the behavior tree, right? The tree would say, hey, go plan. Did it work? Good, run it. Did it not work? Okay, try something else. But these are all like self-contained motion planning algorithms. As far as the joint limits and obstacle avoidance, these can be defined in two different places, right? So we talked about the URDF description. So if I look at the UR gripper, as one example, you see that all of the links that you create in your URDF actually have collision geometries that could point to things like meshes or geometric primitives like rectangles. See here you have like, somewhere in here you have collision boxes for the gripper, for example. That's one way. Actually, in URDF also has a way to load some joint limits. If I search for a joint, for example, you see here the wrist2 joint has certain limits encoded for it for like maximum effort, position, and velocity. But if not that, you can also, you know, ignore the URDF and use your own limits based on the knowledge you have for your robot. Like maybe the manufacturer said these are the limits, but you want to run slightly slower for conservative. So I think most tools let you either read from the description file or bring your own limits. Same for obstacles, right? You can have the obstacles live in the URDF, or in the case of one of these other examples, we actually let me go to a different example here. Oh, sorry, I'm not sharing my screen, am I?
Ah, okay. So I was trying to talk to my team to show your screen because it was not showing there. I thought it was on our side. So it's
no, I will.
Okay.
I'll leave it at that. So URDF contains information, but you can also add it programmatically. Let's move on in the interest of time.
Okay. Okay. Then another question from Nikita Emolenko. Then she says, are there any established algorithms for almost Cartesian planning? She has encountered some problems with real manipulators that struggle to execute perfect Cartesian movements. However, the task doesn't necessarily require perfect lines, and some deviations are acceptable.
Yeah, there's lots of, so at the end of the day, the big reason that Cartesian planning fails is because you don't need your inverse kinematics to meet exactly, like you said, the Cartesian trajectory at every point. There are some algorithms that let you parameterize this easily. One that I keep hearing about lately is called relaxed IK, which lets you, as its name suggests, it lets you relax certain constraints. Mm-hmm. You can also, this is really where the world is going nowadays, but trajectory optimization also lets you do this, right? Where instead of doing, instead of having like hard constraints on a trajectory to like exactly meet them, you can create either soft constraints or not even have them as constraints, but only to formulate this as a minimization problem. So like, give me any valid trajectory that minimizes my distance to the desired Cartesian path. And then it's up to you whether the solution like meets the requirements or not. So there's lots of different ways. I think at the end of the day, it's either getting IK solvers that allow you to express relative tolerances in different parts, or relying on other things like optimization, or even the learning-based approaches, going back to Robert's question.
Yes, I also agree that I think that so it has to go into the direction of learning. I don't see how the proper mathematical resolution and computation of the trajectories can solve this problem, and especially when we have to apply into a real environment where other things can appear at the very moment, and then we have to avoid those things or change the trajectory in some cases. I don't know. What are your thoughts about this?
Yeah, there's one more thing I want to share there. This goes back to actually Goet's question about behavior trees as well. There's something about like when you're trying to run a Cartesian path, you're assuming it fails because you're only giving it one chance to do the path, right? But what you can actually do is if you get yourself stuck like halfway through the path, you can lift off the arm and you can rearrange it so that it's in a better position to finish the second half and then go back in. And this is done very commonly in these like large scale applications. Like if you're trying to like weld an entire airplane wing, like you can't do the single Cartesian path because the robot's workspace is way smaller than an airplane wing. So you actually do have to like do it in pieces. And then it becomes an optimization problem or like a behavior reactive problem for like, how few times do I have to readjust so I can do the whole task?
Okay, then thank you very much, Sebastian. I think that we have to finish here because of the time. Thanks a lot for the awesome project that you have prepared and the presentation. Thank you very much.
Thank you for listening.
Thank you. Bye-bye.
Yes, thank you, Sebastian, very, very much for that very nice presentation. Guys, remember, the rating box should appear now at the chat. So remember to rate the speaker because 2 more left before we pick the best speaker of this year's conference.
Wow, perfect. So before the next speaker hits the stage, let's have some fun.
One more time?
Yes, we're still doing the quiz prize. Yeah, we're still doing it.
Okay.
So yeah, the winner is going to have the Super Sweat box with the I'm a Robotics Developer t-shirt, coffee mug, and stickers. So this is sponsored by the third-party ROS by the constructs. So it works the same. Now we're going to watch a 5-minute video related to the third-party ROS. And at the end of the video, you will see the question related to it. And the first person answers correctly in the chat will win the sweat box. So you may need to go to the page of the sponsor to get the answer. So now let's watch the video, and we will see the next speaker in 5 minutes. So see you soon.